we we are very lucky to have distinguished Professor Antia here to start off our 2026 asset season. And Professor Antia doesn't need an introduction to this audience, but for the benefits of the new students who may not be aware of his long association with us in Department of Astronomy and Astrophysics, Professor H.M. Antia is a distinguished astrophysicist who specializes in solar physics, helioseismology, and the development of numerical techniques for studying stellar interiors. He is currently teaching at the University of Mumbai Department of Atomic Energy Centre for Excellence in Basic Science, CEBS, and having spent a significant portion of his career in Department of Astronomy and Astrophysics here at TFR, Professor Antia played a significant role in our first Indian multi-wavelength satellite on astronomy called AstroSat, primarily serving as a key member for the LXPC team, where I also had a fortune of working with him. And he did the development of the crucial Giant-4 detector simulation for background estimations, calibration software, and data processing pipeline programs, which is still being used for 10 years. Almost all the papers which have come out of LXPC data analysis using his codes and his background simulation techniques and all. With that, I invite Professor Antia to please give us a talk on a space weather. Thank you very much.
Okay, good evening. So I am going to tell you something about the space weather. Now, I should tell you that I am not really an expert in this subject. I have just read something and found that it was very interesting. So I thought we should share something. So that is the thing. So now let us start with what is space weather. So if you look at the dictionary, the weather is defined as the condition in the air above the earth, such as wind, rain, snow, or temperature. So of course, we normally don't worry about weather. We worry only when there is an extreme weather event, such as the heavy rainfall, storm, or extreme temperature. So, and the terrestrial weather is due to response of the Earth's atmosphere to the solar electromagnetic radiation, mainly around the visible and infrared wavelengths. Now, this radiation does not change with time. It is almost constant. So, all the variation that we see is either because of the Earth's rotation, tilt of the Earth's axis, and of course the nonlinear response of the atmosphere to all these changes. So that is there. So now space weather refers to condition which is above the Earth's atmosphere, though some effects may be experienced even at the ground level or even below the surface. So that is there. Now space weather is also due to the sun, but it is controlled by electromagnetic radiation in radio and X-ray, or through the charged particles. So the visible, infrared, etc. doesn't play a role because they don't change with time. So that is not playing an important role. And these are caused by the solar activity, which varies by several orders of magnitude. So in this case, the sun directly drives the space weather, unlike the terrestrial weather. So now the extreme terrestrial weather, of course, has caused a lot of casualty in terms of human life. So far, there is no report of any casualty from space weather, but of course it can still have high economic cost, and even that is much less. So of course partly maybe because we are lucky, and another important thing is that most of the economic losses are borne by the rich countries in the northern latitude. Although of course if there are a number of reports which claim that some astronomical figure for economic costs has been claimed for if there is a strong space weather event, but all those reports are not credible because they are simple extrapolation from something which has happened long back, which accounts for the increased footprint of the technology, but it does not account for the fact that the technology also has improved. So that is not particularly reliable. So we need not bother too much about it. Now a recent example was on November 28th last year, when Airbus grounded about 6,000 A320 aircrafts for software upgrade. So this happened because on 30th October, one of these aircraft suddenly lost altitude and injured some 10 to 15 passengers. And when they did the analysis, they found that it was because some critical data was corrupted in the memory. So, of course, at that day, as it happens, there was no space weather event. So, most likely this was because of the cosmic rays, but the same could have happened by the space weather also. So, of course, in this case, the effect was felt by all countries which had this aircraft. So, this was a more widespread event. Now, extreme space weather has been happening ever since the Earth was formed, but the damaging effects have been noticed only more recently in the last 200 years or so, since the human beings started using electricity. So now with more advanced technology, the vulnerability is increasing, and that is why the space weather is more important now. But that is also an opportunity. Since it is the technology which is affected, you can always improve the technology to take care of at least some part of the effect. So that is the thing. And of course, the main disruptions, as you probably know, are in the power grid operations, communication, satellite, GPS services, radar, air and space travel. So we'll come to these things in more detail later on. So this is also an example of a space weather. So this is the tail of the comet, iron tail of the comet 11, which is fluttering because of the solar wind. So this is not extreme space weather. This is just a normal solar wind. So now we'll come first see what are the drivers of the space weather. That is what happens on the sun. So the solar activity is due to the magnetic field, which manifests at the sunspots. So sunspots are basically dark spots on the surface of the sun where the magnetic field is strong, and because of the strong magnetic field, the convection is impaired, and that's why they look darker as compared to the surroundings. So these are known as active regions, and the whole thing is called solar activity. And the sunspot appears in pairs of opposite polarity, and they are connected by magnetic field lines. So this is a picture taken in UV from the TRACE mission. So you can see the two sunspots, and they are connected by the magnetic field lines. So now these magnetic field lines are visible because the charged particles move along the field line and they radiate in UV. So that is why you can actually trace the field lines. Now this is a relatively simple sunspot. You can have more complicated pairs of sunspots when the opposing regions can come close to each other. So if that happens, then the magnetic energy in an active region can be released through magnetic reconnection. So that happens when oppositely directed magnetic field lines approach each other, and this is mainly driven by turbulence in the photosphere. So this reconnection process, of course, has been widely studied in solar atmosphere as well as in Earth's magnetosphere. Other places, of course, it is more difficult to study that because you don't have that much of data. Now this process can release energy of something like 10 to the 32 ergs and over a period of 100 to 10,000 seconds. So, and the important thing is because of the magnetic reconnection happens in very small volume. So the energy is released in very small volume, which is basically an explosion, and that results in a blast wave which can throw out billions of tons of material, which is known as the coronal mass ejection from the sun at speeds going up to 3000 kilometers per second. So if you compare this with the total solar luminosity, the total solar luminosity is 4 into 10 to the 33 ergs per second. So this is only a very small fraction of that energy. So total energy wise, this is insignificant. So now energy is released in radio, X-rays and high energy protons, which can go up to several GeV, and these are referred to as the solar energetic particles. Of course, there are electrons also, but they have much lower energy, so they don't play an important role. So these are accelerated by shocks, and then of course there is a kinetic energy of CME, which is a highly conducting plasma, which also carries the magnetic field with it. So now the strongest space weather events happen when there are multiple CMEs following each other. So the first CME clears the interplanetary space, and the next one follows quickly through the cleared space, and sometimes the second one can overtake the other ones, in which case they merge, and they are known as a cannibal CME. So these are most effective. So most of the strong space weather events happen through this multiple CMEs. So this is a picture from SOHO satellite. So the left is the UV image of the sun. So that is taken on the 4th November 2003 when the strongest X-ray flare, which measured X45. So this flare has happened here when the active region was close to the limb. So because of that, whatever coronal mass ejection was there, it would have been thrown out in the direction which is perpendicular to the Earth. So we missed that. So of course we were saved. But 1 week before that, there was another slightly less strong flare on 28th October, and that released a CME which is traveled to the Earth. So this is a coronagraph image also from SOHO. So this disk here actually covers the sun. So this generates an eclipse, artificial eclipse. So you can see the corona. So of course this corona is actually, this is a color coded image. Corona will not be red. So this coronal mass ejection is seen coming here. Now this central thing is just the ultraviolet image of the sun, which is just superposed at the center. That is not from the coronagraph. So the active region must have been somewhere here, which released this CME. Now, of course, you should remember that this is a projection. So the part of the CME which is coming directly towards the Earth will not be seen because that will be behind this disk. So only when it spills over the disk, you will see the thing. So from that, you have to infer where it is going. So that is there. So the coronal mass ejection will be effective only if it is emitted by sunspot near the center of the visible disk. When it is near the limb, it will not reach the Earth. So that is there. So now let us go. So this is a X-ray flux from the GOES satellite. So this actually is real-time updated almost every minute, and anybody can see the data. So you can see that there are two flares. These are in two different wavelengths. So there are two flares which have happened one after the another. And of course, if you look at the right side, there are these things like M, X, etc. So this M means this is M class flare, X means the X class flare, which are the strongest flare. And of course, each of them is divided from 1, 2, 3 up to 10. So for example, this flare will be X10, while this one will be X2 roughly. And these are all M class flares. So that is how you detect the flares. So the flares are either detected through the X-ray flux or through the UV image. So these are constantly monitored. So you will know immediately. Of course, you will know only after 500 seconds, but that is when you will see the flare. So this is so the CME propagation in the interplanetary medium can also be tracked using the interplanetary scintillation. So this scintillation is basically just like if you look at the stars through the atmosphere, they scintillate or flicker. So that is because of the turbulence in the atmosphere. So similarly, the turbulence in the interplanetary medium, the radio sources also scintillate, and by measuring that, you can measure the strength of turbulence along the line of sight. And if you track many sources, then you can do something like a tomography, and you can get an image of the CME. So here, this red is the normal solar wind. This is the CME, and Earth will be somewhere here. So this is data taken from the UTI radio telescope by Manoharan and his colleagues. So that is, so we can even track the CME. And then of course, this is the well-known solar cycle. So that is the number of sunspots and hence the magnetic field has a well-known quasi-periodic variation with a period of 11 years. So the level of solar activity depends on this number. So if the solar activity is high like this, there are more chances of flare. Of course, that doesn't mean that the flares cannot happen when it is here, because for that you only need a few sunspots. So you don't need many of them. So that is a slightly different thing, but there is certainly a correlation between the level of activity and the level of flares and other things that are happening. So this is all the 25 solar cycles which have been measured properly from 1750 until now. And these red dots below are some of the space weather events. I have not used any particular consistent criterion to select them, so they are just some random choices. So some of them I will describe in more detail later on. So now we come to the effect on Earth. So whatever has happened on the sun, of course, it will affect the Earth. And the first thing I should tell you is that there is no way as of now to predict the solar flares. So the solar flares will be known only when you see them in the ultraviolet image or in the X-ray flux. And of course, all the electromagnetic waves travel at the same speed. So which means that as far as X-rays and radio flux is concerned, there is no warning. They will reach the Earth without any warning. Now the protons, of course, depending on the energy, they can reach up to few minutes to an hour later. But most of the flares are not accompanied by a proton flux. So that also is not that easy to get. Mostly you will see it only when it arrives. Before that, you will not know whether it is happening or not happening. So the only thing which you can actually predict is the CME. So CME takes something between 15 hours to a few days to reach the Earth because they travel at a much slower speed. So that gives an enough warning, but it is still difficult to predict the geo-effectiveness of a CME until it actually reaches close to the Earth. So I will tell you why that is there. And another major problem is that when the solar activity is very high, there are strong flares and CMEs every day and sometimes more than one per day. So, and of course, all of them will not be geo-effective, only a few of them will be effective. So it is very difficult to predict which one will be. So that is another problem. Although we will know that some CME is going to come, but how effective it will be is a difficult thing. So now we'll see each of this, what happens to that. So the solar radio bus can jam a radar because they also use the radio frequency and it can block all radio communication because basically the flux in the solar burst is much stronger than what is there in all these things. So they can completely jam all the thing, and this can happen at all latitudes, but it can happen only during daytime because it is a line of sight thing because the electromagnetic waves are not bent by anything. So only during daytime it can happen, and it can also disrupt the GPS signal because GPS signal flux is also less than the typical burst, strong solar burst. But there is a small advantage because GPS signal is circularly polarized and it also has a characteristic waveform. So if the receiver can lock onto the waveform, then you may still get the signal. But if it cannot lock, then of course you will not get anything. So that is how the GPS works. Now, X-ray flux can ionize atoms in the ionosphere, which will add to the ionospheric disturbance from other effects, which we will come to. So this, yeah, so now the solar energetic particles. So these are charged particles, so they will be deflected by the magnetic field of the Earth. So they predominantly go towards the pole, or rather towards the geomagnetic pole. And so they, in that polar region, they ionize the upper atmosphere. And therefore, of course, because of this ionization, it gives to the so-called polar cap absorption events. So this disrupts radio communication over large range because the lower range radio communication happens through line of sight, but the longer range radio communication, the waves have to be reflected by the ionosphere. So when the ionosphere is disturbed, it will not reflect, it may absorb these things. So because of that, this communication is disturbed. Of course, nowadays we don't use radio communication too much, but still it is useful in the polar region. So the aircraft, ships and facilities in the polar region depend on these frequencies. And some airlines also operate flights over the poles because that offers a shorter and also better path in the sense that the headwinds are less, mainly between US and China. So these flights have to be rerouted to lower latitudes, and that of course will cause some economic loss because not only once the flight is rerouted, it will need additional fuel, and which means that they will have to either offload some passengers or some cargo, and in the worst case, of course, if they can't cover the distance, then they will have to have an intermediate halt. So all those things disrupt the thing, and because of that, there is some economic loss. Now the important thing, of course, I think I'll come to that later on. So this happens because the federal regulations require that the flights have to maintain communication with ATC over the entire route. Now there are no ATCs in the polar region, so this communication has to be done through the satellites. So geostationary satellites are used to do the thing, but the geostationary satellites are on the equator, so they are not visible once you are above 82 degrees latitude. So then you have to rely on the radio communication. So if the radio communication is blocked, then of course they have to avoid the high latitude region. So that is there. And these PCA events are fairly frequent and they also last for a long time. They can last for 1 week also. So the flights disruption, and this is actually a major economic loss from the space weather events because each flight disruption will cost significant amount and there are hundreds of flights. So that is a significant thing. Now the charged particle flux can also increase the exposure of radiation for air and space travel, particularly outside the Earth's magnetosphere. So in the low Earth orbit, it is still not so bad, but for example, in the International Space Station, whenever there is a strong space weather event, all the astronauts hide in the Russian module, because that is the only module which has sufficient protection against radiation. So, so they don't have otherwise. So that is the thing. So that is there, and of course outside the Earth's magnetosphere it is much worse. They have to just expect that the space weather event will not happen. Yeah. Yeah, of course. Yeah, ham radio fellows will of course be affected because they depend on the same thing. Yeah. Of course, they will. No, this is common in the polar region. It is a polar cap absorption event. So in the polar region, it is common. Yeah. No, they are common, fairly common. I mean, I'm not saying every day it will not happen, but it will happen sometime in a year. So and of course, during the high activity phase, it can happen many times in a year also. So that is there. So the charged particle flux can also cause this I already talked. So now, so this is just a schematic picture, obviously not on scale. So there is a solar wind coming from here. This is the Earth, and this is the magnetic field of the Earth. So because of the solar wind, the magnetic field is distorted. So the sunward side it is compressed, and on the opposite side it expands. And this is the shock. So these solar wind particles go around that. So they will not enter the Earth. So this is of course the normal solar wind. When the CME comes, I don't have a picture of that. In that case, of course, the CME has a much higher density and also much higher velocity. So it will compress the field much more. So if the field is compressed much more, then what will happen is that the geostationary satellites, which are at about 6.5 Earth radius, they may be outside the Earth's magnetosphere. So in that case, they will have much higher radiation level. So they will be affected much more by the radiation field, and that's why all these geostationary satellites have much higher level of radiation hardening, because otherwise they will not survive. So of course it seems to work, because so far I think in all the decades, as far as I can find, only 1 or 2 communication satellites have been disabled by space weather. So mostly they have survived. So whatever radiation hardening they are doing seems to be effective. Now the CME can also has a magnetic field, because by the Alfvén theorem, any conducting charge plasma will carry the magnetic field with it. So they carry the magnetic field from the sun. And if this field is oriented opposite to the Earth's field when it collides with the Earth's magnetosphere, then a reconnection can happen. So if the reconnection happens, then what happens? The field in the CME will be connected to the field in the Earth. So therefore the plasma of CME will flow into the Earth. And that is going to cause a severe geomagnetic storm, because you have much larger flux of charged particles in that. So this is the main driver of the space weather. So and is here the mass loss rate? No, it doesn't depend on the mass loss rate. It mainly depends. See, the CME will be carrying something. Of course, what is the amount of mass which is there in the CME will of course be important. But the more important is the orientation of the magnetic field. If it is not oppositely directed, then the reconnection will not happen. So in that case, of course, it will not enter into the Earth. So the reconnection has to happen, and that is the main problem. So you don't know what is the field of the CME until it reaches the L1 point, because at Lagrangian point L1, there are some satellites which measure the magnetic field and other properties of the solar wind, and that gives us a warning of only 15 to 30 minutes. So, Oh, that is fairly large. It is fairly large. That will be, I mean, several tens of degrees. Of course, there may be some turbulence, but the question is, once the field line connects, something will come into the Earth anyway. No, it's certainly not totally random, because the thing is the density is much less. and the whole thing has been ejected together. So it is not the turbulence, see, it is not turbulence in the photosphere. So that turbulence level is definitely much less. Some turbulence will of course be there. It cannot be totally laminar, of course. You are right. But there is a thing and it does reconnect, and that is where the field can be measured. So obviously it is not turbulent because the field is measured. So that is there. So that is the major problem. And now the flux of charged particle in the ionosphere, of course it will lead to the communication and navigation problem because ionosphere is disturbed. And then of course this introduces a ring current in the ionosphere which reduces the strength of the geomagnetic field. So that is another thing, and this can also severely affect as a long distance radio communication. It also affects the GPS signal because GPS signal is affected because the GPS signal has to come through the ionosphere. So when it is traveling through the ionosphere, the speed of the thing will be less than the speed of light in the vacuum. So there will be some delay in the thing. So that delay has to be accounted for. So of course ionosphere is there all the time. So normally what is done is that they use some average model of the ionosphere to correct for the delay. But when the ionosphere is disturbed, of course that model doesn't apply. So it is going to introduce an additional error. Of course that error is relevant only if the GPS receiver can lock onto the signal. If it doesn't lock on, then anyway it will not see anything at all. So because that can also happen, because if it is severely disrupted, then it may not lock at all. So in that case, of course, nothing will be seen. So, yeah, I will come to that. We will see how much it can lower. See, it can lower by several %, the whole geomagnetic field. So it is definitely not much smaller. So that is a measured quantity. So there is no doubt about that. So that is there. So we'll come to that. Now so where was I? So that is reduces the strength, and of course the GPS signal will also be disturbed. Now the geomagnetic storm also causes the Earth's magnetic field to change with time, and any change in the magnetic field by Faraday's law will generate electrical current in the circuits, or current in the electrical circuit. So this can affect the equipment in the satellite or even on the ground, and these are referred to as geomagnetically induced currents. So any long, of course, this is applicable only to the ground. Any long conductor like a power line or a pipeline is vulnerable to induced currents, and pipelines in the polar region are eroded faster because of the induced currents. Now the east-west alignment is supposed to be particularly sensitive. Now transformer in the power grid are particularly vulnerable because the power grid operators are most worried about the transformer, because what happens is that the transformers are designed to handle AC current because that is what they are transmitting. But the induced current is essentially DC. Although of course the magnitude will be much smaller than what a power thing will transmit, but it is DC. So that causes overheating in some parts, and in the worst case it can catch fire. There are several transformers have been burnt during the space weather events. So that is the biggest worry of the power grid operators, because if a ordinary transformer burns, of course they will have a replacement and they can replace it in some reasonable time. But if a big transformer is damaged, then of course there is no replacement. And these are all custom made transformers where the delivery time is of the order of 1 year. So of course even if they do some emergency, it will probably come in 1 month. So you can see what will happen in that case. Of course that has not happened so far, but if such things happen, then people will be without power for something like 1 month. So that is the biggest worry about the power grid operators. So now the energy deposited in this upper atmosphere also heats it up and it expands. So because of the expansion, what happens is that the air or whatever is there in the atmosphere at the lower altitude comes to the higher altitude, so that has a higher density. So because of which the drag on the low Earth orbit satellites increase and their lifetime is reduced because they tend to lose height faster. So the solar arrays are also degraded by the intense radiation. The 1970 premature destruction of Skylab was due to higher than expected solar activity. Now the charged particles can also lead to charging on the satellites, and that can also discharge, damaging the circuits. Yeah, so this is the strength of the geomagnetic storm is measured by so-called Kp index, which is actually P is for the planetary, so it is planetary K index. And of course, as usual, it is on the log scale with a maximum value of around 9. So of course, this is obtained by averaging over something. So this is available since 1932, and during that, since then, there have been about 250 days when the Kp index was higher than 8. So a Kp index of 5 is supposed to be the low geomagnetic storm. So this distribution is shown along the calendar month. So this is January, February, this is December. So you can see that there are two distinct peaks there, which is in March and September. So these are during the equinoxes. So this is known as the Russell-McFerron effect. So this is because during the equinoxes, the geometry of the field is more favorable for reconnection. So that's why the geomagnetic storms happen more frequently near the equinox.
Skylar came down in 79.
What?
Skylar was not 79. Because he did an experiment with it in 74.
Oh, so then maybe there is some mistake there, but sometime. Yeah. I think I read it somewhere, but that may be a mistake there. Yeah, so lastly, the only manifestation of space weather which can be seen by us is the aurora. So these are colorful displays of light caused by the charged particles interacting with atoms and molecules in the upper atmosphere at a height of something between 100 to 500 kilometers. So these displays have been seen at high latitudes for a long time, even when nothing was known about space weather, and there are records going back more than 2000 years, mainly in China. So these things have been recorded. Now the auroras are primarily seen at high magnetic latitude. So the magnetic latitude is what matters because that is the latitude measured from the magnetic pole. By the way, the magnetic poles are reversed. The south magnetic pole is near the north geographic pole. So, so that is the thing. So it doesn't matter, but they are still about 10 degrees from the geographic pole. And of course, they keep changing. So the geomagnetic magnitude or latitude also keeps changing. So, but during the strong geomagnetic storms, they can be seen even from tropical regions. So around 70 degrees magnetic latitude, there are auroral ovals which are there all the time. So the auroras below that, you can see aurora almost every night. And I think this is a picture taken from the space for the auroral ovals, which is I think centered near over Canada at that time. So now the colors of the aurora, of course, depend on the species or atoms or molecules which are excited. Now the red ones are formed at the high latitude, which are due to atomic oxygen line at 630 nanometers. And the more frequent collision at lower altitude suppresses this line. Now instead the green line at 557.7 nanometer is seen also from atomic oxygen. Now both these are forbidden lines with a lifetime of 2 minutes and 0.7 seconds. So which means if the collisions are more frequent than this, then of course they will be collisionally de-excited and you will not see the lines. So at even lower altitude, the blue lines at 428 nanometer due to molecular nitrogen or ionized N2 dominates. So now you have both all the three RGB are there. So with this combination, you can get almost any color. So that is why you get all kinds of colors in the aurora. So before I go to that, this is a map of geomagnetic latitude. So of course, as I told you, pole is 10 degrees below the actual geographic pole. So that is in the Canada. So that's why in the North America, the geomagnetic latitude is about 10 degrees higher than the geographic latitude, while in the Europe it is slightly lower. So that's why auroras at the same latitude are seen more often in US than in Europe. And of course, for those of you who know this complicated geometry, here is the South Atlantic anomaly. So that is there. And so this is of course a picture of aurora from Iceland. So now we come to some individual space weather events. So this is the first solar flare was discovered by Carrington on 1st September 1859. So he observed a sudden brightening in some active region. So those days there were no cameras. So this is actually a picture from the original publication of Carrington. So he has drawn this sketch of the sunspot. Of course, no polarities were known that time. And if you can see, there are two lines marked here. So this is where he saw the brightening. So first thing you can see is that this is only a very small area, and that is the signature of the magnetic reconnection, because that happens only in a small volume. So that is why it leads to an explosion. So this is where he saw the brightening. This was, of course, the first time. So that was the first solar flare, but after that, the next day, there was a severe disruption in the telegraph network. So the telegraph network was established some couple of decades before that, and the operator suddenly noticed that this thing, of course, they had been noticing this thing earlier also, but that day it was particularly severe, and many operators got shocks because this telegraph thing was operating through a battery driven thing, single wire. On both ends there are battery, and the return current is through the ground. So that is how they used to operate. So some of them got shocks, so which is of course not expected when it is battery driven. And then of course some cases the paper also caught fire, and all those things happened. Then some of the operators, since he got shock, he disconnected the battery. So then he found that even after disconnection the message was going. So then he told the operator at the other end that you also disconnect. So he disconnected, and after both the ends it was disconnected, still the message was going. So that is of course the ultimate green technology. So you can see that. So that is what happened. So now of course it was also accompanied by massive display of auroras extending to tropical regions in Hawaii, Cuba, Jamaica, and San Salvador. So in this aurora, this happened around midnight, and of course in the northern latitude it was very strong, and people could read newspaper with that. So that is there, and that time many people were camping in the Rocky Mountains, and they suddenly woke up in the middle of the night and thought that it is morning, and some of them even started preparing for the breakfast. So that is what happens with aurora. I'm coming to that. That is the next thing. Yeah, so the first CME was discovered only in 1971, but assuming that the CME was ejected soon after Carrington saw the flare, so it reached the Earth in 17 hours and 35 minutes, which gives an average speed of 2300 kilometers per second. So now this is believed to be the largest flare that is recorded so far, and of course auroras were widely visible between intermittently from 28th August to 4th September. So which means there must have been multiple flares in CME. This is what typically happens. One may be very strong, there will be many other which are not that strong. So that is there. Now what Gopu said, the Colaba Observatory in Bombay, which is about 2 kilometers from here, which was, now it is not, so recorded the magnetic disturbance measuring a dip of 1600 nanotesla in the horizontal component of the magnetic field. So this is 4% of the normal magnetic field. So that will tell you how much the Earth's magnetic field changed. So that is there, and this was probably the only magnetic observatory operating in the tropical region, and it has played an important role in estimating the early geomagnetic. Of course, many other observatories in the high latitude region, but in high latitude region they are in the thick of the action, so the magnetic field changes very randomly, and it is difficult to get a good estimate of the strength of the picture from the, the record from the Colaba Observatory of 1859. So no, that is because most of the changes are happening in the higher latitude, there are lots of events happening. In the lower latitude, only the average effect will be felt, because most of the action happens at the higher latitude, because all these charged particles, all the things are there in the higher latitude. Even the auroras are also there in high latitude only. So everything is at high latitude. So that is where I don't have the record, but those things will show many fluctuations. Well, here you can see that there is a clear dip. So that gives a measure of the effect of the storm. And even now, this is what is used. Only thing is now they do an average. Yeah.
How long did that?
No, by this time it had become more or less normal.
No,
No, this is days. This is September 1, 2, and 3. So this September, these are hours, but this is going through cycle. So no, this is over 3 days. So even now all the yeah. Huh? Yeah, first dip, yeah. So these dips are used even now. All the DST index and all the indexes are measured from the dips. Only thing now they do is that they take average over a few tropical observatories, and they also average over some 3 hours or something. So this, so that's why those things will be somewhat lower than this thing. So that is, so that was the Carrington flare. So now we come to the next major event. So that was on the next cycle, which is the 4th February 1872. So that also caused disturbance in telegraph and all those things. By now the telegraph network had spread all over the world, and there were submarine cables also. And the Colaba Observatory reported a dip of 830 nanotesla, so which is about half of the Carrington thing. Now the important thing is that auroras were very widely reported from as far south as Bombay, which was at 10 degrees magnetic latitude, Jaipur, which is in Orissa at the same latitude, Cairo, Khartoum at almost 6 degrees magnetic latitude. And all these reports were from telegraph operators, because the telegraph operators knew that there is a correlation between the disruption and auroras. So whenever the disruption happens in the night, they would start looking for the auroras in the thing. So these were all reported by them. And of course, even at other places in India, Bhavnagar, Allahabad, Lucknow, Darjeeling, everywhere the auroras were reported. Now, unfortunately, of course, there were no cameras in those days, so there are no pictures, but fortunately, Times of India was there. So this is the report on 6th February, page 2. There is this report from Aurora Borealis, so you know that it happened. So that is there. Of course, after that, I don't think there has been any record here. So now we come to the next century. So the most intense geomagnetic storm of 20th century happened on 13 to 15 May 1921. So of course it was probably driven by many CMEs, etc. Of course those were not known that time. So apart from of course the normal disruption of telegraph and telephone things, there were many fires were also caused. And these fires were, because by that time there was a good network of electrical network as well as the electric trains were also there. So there was many things to be disrupted. So many fires were caused. The telephone exchange at Karlsbad, Sweden was destroyed. The railroad station at Brewster in New York State was also destroyed. Long distance telephone lines were burnt in New Brunswick, Canada, and a control tower about 1 kilometer from New York Grand Central Station was also destroyed. Now this fire happened a few hours after the peak storm, so some people believe that it was not caused by the space weather event, but of course the disturbance was still there. It had not fully quietened. So of course it is an open question. So the magnetometer now by that time had shifted to Alibag, because 1900 Colaba got electric trams. So it had to be shifted. But somehow that went outside the scale, even though it was only, the scale was only 400 nanotesla. So they had probably tuned the sensitivity at that. But there was another observatory at Apia in Samoa, which recorded a dip of 920 nanotesla. So of course, most of the magnetometers, even at higher latitude, all went out of the scale at that time. So, and of course, the auroras were seen from various places. Now, this is the more interesting thing, the solar storm on 23rd May 1967. So that started with the largest recorded solar radio burst of 20th century, causing an interference at frequencies from 0.01 to 9 gigahertz. So that covers almost the entire radio band. And intense X-ray flux and also the solar energetic particles caused a polar cap absorption events and disrupting the radio communication in polar regions, which lasted for 1 week. So there was also a loss of signal between satellite and ground station. Now the radio flux at 1.4 gigahertz was recorded at 85,000 solar flux units, So this is about 10 to the 4 times the Jansky, which is used by radio astronomers. So this would be about 1 giga Jansky. So that was the kind of flux which was there, and of course the maximum Kp index, etc., were recorded. So now now this is the more interesting part. So this happened during the height of the Cold War, and the radar system operating at 440 megahertz in sites in Alaska, Greenland, and UK were jammed. And the Cold War military commanders thought that this is an act of war, and nuclear armed bombers were ready to take off. So this is what happened, and this is reported in this paper, which has appeared in Space Weather, and half the authors in the paper are listed as retired from US Air Force. So this is probably an official account of the event. So of course this appeared almost 50 years after that. Probably that was the time when these things were declassified. So that is there. So, and just at that time, NORAD, which was an arm of the US Air Force, which was prepared, which was actually launched for predicting space weather event. So they issued a space weather alert, because as I told you, the radio things cannot be predicted because they will be seen only when the flare is there. So they of course knew it only when it happened, so they informed, and because of that, fortunately good sense prevailed and the fighters did not take off. Of course, what is not written here is whether President Lyndon Johnson was informed and whether he approved the strike. So that part has probably not been declassified. So something must have happened, but that is not declassified. So similar jamming event had happened during World War II in 1942, and Allies thought, they again didn't report it because they thought that when it happens next time they will bomb Germany, but of course the next time didn't happen. So, but the important thing is, because of all these things, there was an improved priority and funding for the study of space weather. So because if something happens of strategic importance, then of course the politicians release the funds more easily. So that is what happens. Now this is another one. So that is the 4th August 1972. Actually, I think this was the flare which was studied by Jyoti Nivetya. I think you might know. So that is there. So this again, so this recorded the fastest CME, which took only 14.6 hours to reach the Earth. So that is the record time. So with an average speed of 2850 kilometers per second, and of course there were a large number of things and strong radio bursts, etc. Now during this storm, a defense satellite communication system mission ended due to power failure, and then the US Air Force Vela satellite, which was launched to detect nuclear tests on the Earth, it mistook this disturbance as an explosion, and of course that was resolved. And of course the astronomers will know that this Vela satellite, although it didn't detect any explosion from the Earth, but it detected many explosions from the sky, and which are known as the gamma ray bursts. So now again, this happened during the end of the Vietnam War, and the US Navy had mined the sea around Vietnam, and on that day the Air Force pilots reported seeing 20 flashes from detonation of these mines. And afterwards they found that almost 4,000 mines were detonated. So these were magnetically sensitive mines. So the idea was that if a ship passes over it, since ship will have a lot of iron, it will disturb the magnetic field and that will detonate the thing. But of course it was obviously a design fault, because the sun can change the magnetic field by much more than what the ship will do. So this was not realized. So that is the thing. So after that also, although of course the solar alert, etc., were all there, but the military fellows were not totally convinced. They were thinking that Vietnamese fellows might have done something. So they went back to the National Academy of Science experts and sat with them and did the calculation. And after that, they were convinced that all this happened from the sun, and Vietnamese fellows were not responsible for any of that. So that is there. And of course, I don't know what effect it had on the war, because the Vietnamese probably did not know that the mines have been detonated. And in any case, the war ended within 6 months of that. So that is there. Now this storm occurred exactly between Apollo 16 and Apollo 17 mission, and that saved the astronauts. If the astronauts were walking on the moon, they would definitely not have survived. Even in the lander, they would not have survived. And if they were in the command module, which was orbiting, then the estimate is that they would probably have survived with some serious medical issues. So that is the problem with the space travel beyond the Earth's geomagnetic thing, Earth's magnetosphere. So this is of course an important thing because people are now planning missions to Moon and Mars, and I don't think they have protection against the strongest storms which are possible. Not geomagnetic, because this is outside the geomagnetic thing. So it is mainly the direct proton flux, because the CME, since it travels very slowly, it will not penetrate the shield. So that is not, it is the high energy protons which will do the thing. So that is the thing. So okay, so the next thing is 1989, 13th March. So that also of course had some things. Now in these days, the ground induced current across the hydro-Quebec power system in Canada caused a transformer glitch, and that caused a generation loss of 9.45 gigawatts of power, and the grid collapsed within seconds, causing a blackout of about 9 hours in Quebec, affecting about 9 million people. So during the same storm, another transformer in the Salem nuclear power plant in New Jersey also failed. So these failures prompted extensive review of equipment, because people were obviously worried, because if these things happen, then there will be problems. So now I believe they have changed some things in the transformer design, and apart from that they have introduced lot of SOPs. So basically they keep track of the ground induced currents all the time. So whenever it goes beyond something, they try to adjust the distribution in the grid to take care of that. And I think finally, if nothing works, they will probably disconnect the transformer, because that will at least save the transformer even if the grid collapses. Because if the transformer is saved, then can bring back the grid pretty fast. So all those things are there. That is why this kind of major things have not been seen after that. So the number of satellites were temporarily disrupted, including GOES and Space Shuttle Discovery. Another storm on 16th August caused the halt of all trading on Toronto Stock Exchange. So everything can be affected. So now now we come to the last 21st century. So this is the first storm when all the satellites were in place for observing the different parameters of space weather, because the last thing was SOHO, which was operational in 1996. So all the previous storms happened before all the things were in place. So this is one of the most well-studied solar storm. So there were of course 3 big active regions, and there were a huge number of flares during that, and I have also already shown you the pictures from those things. So that of course is already there. So now let us go to what happened. So the CME was detected by Mars Odyssey spacecraft, and one of the instruments on board was disabled. Now ironically, this instrument was supposed to monitor the radiation environment near Mars. So that disappeared. Then Ulysses spacecraft near Jupiter, Cassini en route to Saturn, and finally in April 2004, Voyager 2 at a distance of 70 AU detected the CME. So which means the CME traveled almost all the way to the heliosphere. The heliosphere boundary is around 100 AU. So that is the thing. And Japanese EDIOS 2 satellite was permanently disabled, and almost 50% of the operational satellites, including WMAP, SOHO and ACE, were interrupted. Now SOHO and ACE were supposed to monitor the space weather, so you cannot switch off the instruments on that. So one instrument on ACE was permanently degraded. Now some instrument on the space station was switched off because they can afford to do that. And during this time, 36 of the 70 spacecraft which failed in 2003 happened during this storm. So you can see that this knocked off almost 30 spacecraft in that. And another important thing is US Air Force keeps track of all space debris, because they want to warn these other spacecrafts of possible collision. So they lost track of almost 50% objects in the low Earth orbits. Of course, some of them might have fallen to ground, but not all. That is because they suddenly changed the altitude. So it took them a week or more than that to recover all the things. So this of course was in 2003, when the number of satellites was comparatively less. If this happens today, then within 2 or 3 days there will be a collision between some satellites. So then once the collision happens, there will be 1000 debris generated. So that will create a more problem. So that is another problem. Now the polar flights were suspended and there was a communication blackout over Antarctica for 5 days. And the augmented GPS system had to be disabled for 30 hours over USA. When between 19th October and 5th November, aviation radio communication was disrupted almost every day for some time. And considering the radiation level, the Federal Aviation Administration issued the first ever and probably only one advice that all the airlines should stay below 7500 meters when flying above 35 degrees magnetic latitude. So that is to avoid the high radiation dose. So of course this was a much stronger event, but even during the normal strong events, the polar flights, people flying in the polar flights can accumulate a dose which is several percent of the annual safe limit. So which is particularly important for crew because they keep flying back and forth many times. So in about 10 flights, they can reach the annual limit. So that is there. Of course, this was much stronger. So that is there. And now I have talked about augmented GPS. So this augmented GPS is because, as I told you, GPS is affected. Now, as of now, all the aircrafts have the traditional radio navigation system still in place. So even if GPS doesn't work, they can still navigate. But the problem happens near the busy airports. So because what happens is that to take care of this, there is some minimum distance which has to be maintained between two aircrafts. So that limits the number of flight operations that happen. Now if GPS is operational, then the the aircraft positions are known more accurately, then they can reduce the minimum distance without compromising the safety. So that allows them to have more operations. So if that doesn't work, then of course it will suffer. So some flights would have been diverted and others would have probably been cancelled or whatever. So that all happens. So this augmented, I don't know, I think I probably didn't explain what is the augmented GPS. So the augmented GPS is to counter this. So they have, so in Europe, US and Japan, they had a network of ground stations, which are of course at a known location. So they keep monitoring the signals from the GPS satellites. And of course they know where they are, so they can correct for that. And using that correction, in real time, they can make some model of the ionosphere to correct for the GPS signal. So that is the augmented GPS system, but even that failed for 30 hours. So that didn't work. Now, of course, this is in 2003. So, of course, I don't know how many people are following GPS. So, in 2003, the GPS was operating at single frequency. So, now I think 2013 or so, they have started operating on dual frequency. So, now we have a dual frequency GPS. So, they will get two different frequencies. So, they are affected by different amount. So, using that, they can get a better estimate of the thing. So, maybe this may not happen now. That is possible. So, these are some of the mitigation measures which have happened because of this. So, that also has to be taken into account. So, there was an hour-long power failure in Malmö, Sweden, and interestingly 12 transformers were damaged in South Africa. Now, South Africa is of course not at very high latitude, so they were probably not implemented all the measures which were there, but they were probably affected because they are close to the South Atlantic anomaly. So that is there, and now, yeah, so this is the last measures thing. I think I can have 2 minutes. Yeah, so this is the last major storm which happened on 10th, 11th May 2024, when of course there were some flares and all. Now the important thing was that auroras were visible over a wide range of places, including Hanle, Oman, which is at 18 magnetic latitude, Canary Islands and Hawaii. And of course, this cannot be compared with 1859 or 1872 because now we have better technology and all these things are actually seen at astronomical observatories in camera. It is not clear whether they were visible to naked eye. So that is a different problem. So this cannot be compared with that. But of course, although I don't witness that, but I am told that this extensive aurora coverage caused a storm on the social media, and there was a thing. So that is there, but of no major disruptions of any services, only some GPS controlled tractors in US. These farmers use GPS controlled tractors for planting and harvesting operation. So they need an accuracy of some 10 centimeters or something. So even though they were having dual frequency GPS, that was not enough. So they had to delay, I think that time they were supposed to plant. So the planting has to be delayed by 2 days. So that was the only thing. And of course there were some satellites, etc. there. So basically it means that, of course I can put the, so that means that whatever measures we have been implemented, this seems to be working at least to some extent, because the number of disruptions has been coming down, although the storms are there, at least at a comparable level. So of course the other predictions which are very high thing, that may not work out. So this is the final slide. This is a picture from Hanle. So all the auroras which are seen from low latitude are red, because that is what happens at the highest altitude of 500 kilometers, and they will be some 1000 kilometers away. So if you have to see that, you have to have that much clearance. So of course, if you have your AQI of 300 or 500, you certainly can't see anything. So that is there. So I think, thank you. So.
Very engaging topic and talks. Open for questions.
You mentioned the CME of 2015 that was detected by the UT Cosmic Ray Observatory, which there was a reconnection event in the upper atmosphere, which caused well, it was described as
there
a
are
crack in the
many things.
No, did that not cause any other disruption?
No, there was absolutely no disruption or anything. That was an extremely small event. I don't think there was, of course, auroras would have been seen, but beyond that, nothing was there. No, this didn't cause any disruption. So that's why I have not mentioned it.
Yes. Sorry.
Because that way, of course, CMEs happen every day. So that is not.
That could be an early warning system for CMEs.
That I doubt very much, because they have seen only few events and thousands of CMEs have occurred. So I mean, so that I don't think can be any predictive measure. I doubt very much. Another thing is that, of course, they did some precursor, but the problem is there is some feature of the precursor. The problem is they have to go back to whole 30 years data and see how many times their signal was seen, even when there was no CME.
But what about neutron monitors? There is a worldwide network of those.
Has
anyone looked for correlations with CMEs?
No, that of course correlation, that is the Furbush decrease, that is of course there.
That is regular.
Furbush decrease of course is there, that is well known. So Furbush, I don't know when it was at least some several decades ago. So no, that of course is there, but all those things are recorded on the earth. So that happens after the thing has landed. So they don't have predictive value. No, those effects are there. Of course, I have not covered all those things because those are important only for science. So no, those are of course there. No, UT also detects the big dip. In fact, they detect a bigger dip because the muons is more sensitive. Yeah. So they detect a bigger dip. So no, for example, 2003 storm, there is a big dip which was detected. So those are of course there.
Thank you.
Yeah.
You mentioned Antia, so it was very interesting summary. So this one of them you mentioned that was reaching up to something like close to 3,000 kilometers per second.
Yeah.
So for many of these major ones you mentioned, how many of them have the speeds measured or recorded? Are they?
No.
Was that one?
No. Just see, all the CME speeds are recorded when they are seen in coronagraph. So that typically goes slightly more than 3,000 also. But when they travel across the interplanetary space, of course they decelerate. So this is the average speed which is taken just from the origin and the final and divided by the distance. I say distance divided by the time. So this is the average speed. Okay. So that of course can be measured for any CME. That is not, because you know when the CME was happened and when it reached the Earth.
Right. Okay. So that is not particularly exceptional in terms.
No, that is not exceptional. I mentioned because some of them are very fast. So the other things can take days also. Yeah. See, some of the CMEs which are emitted at a lower speed, they are actually accelerated by solar wind. No. So all those things happen, of course, but they are typically not very effective. It is only the ones which are traveling fast are the more effective ones.
Very nice talk, Antia. Just a follow up. Will it be useful if we can get a distribution of CMV at, kind of various locations in, along the various line of sight directions?
Oh, you mean in the solar system?
Yeah.
Oh, it will definitely be possible.
No, so will it be useful for anything?
No, for space weather it may not be useful because we are only interested in what comes to us.
Right.
We are not interested in what goes in other direction. So that will not be interested, but I am sure the database are there, so one can find out. That is.
No, I was thinking about the DM fluctuations we see in when we monitor pulsars.
Oh, I said that is why you are asking.
Yes.
Space weather it is not relevant. But yeah, for that purpose, I am sure you can get it. But there is a catalog of CMEs available, which is maintained by NASA. In fact, our friend Gopal Swami is doing it.
So I was thinking about.
So they maintain all the CMEs. Of course, the CMEs which happen on the other side of the sun, some of them are seen, but not all of them will be seen.
Okay.
So the CMEs which happen on our side, of course, are seen.
Now, I was thinking about interplanetary missions when they come, especially human and all that, this will become interesting.
No, right? As far as human things is concerned, CMEs are not important because CME will not damage anything. Okay. Because they are traveling at 3000 kilometers per second, so they will not penetrate the spacecraft.
Okay.
So there it is the proton flux which is important. So the proton flux is what matters because that goes up to GeV. So that will penetrate through significant thing. It is basically an economic problem because if you want to shield, then the weight will increase, and which means you need a more stronger space launch, whatever. So because of that, they have to do some optimization.
Okay.
So I doubt very much that even for example, the Artemis mission, which is supposed to go, I don't think they have full protection against even the strongest event which have actually happened. Forget about what is possible. Okay. That will not be the case because this requires too much of things. So they will be dependent on prediction or something or the other.
Thank you.
Okay, so.
Is there any difference in hemispheric, southern hemisphere versus northern hemisphere in terms of the major event distributions? I mean, southern versus northern hemisphere.
Statistically, if you average over a long time, there is no difference. But any given time, there is an asymmetry between north and south thing. There are many times when the northern hemisphere or the southern hemisphere, one of the two has higher activity. So that, of course, happens. But I think if you take a long-term average, I don't think there is any asymmetry.
Baseline now, what, 100 years?
Yeah, definitely, yeah. No, that's why I'm saying long term, I don't think there is any asymmetry because some cycles it is the other way around, some cycles it is this way. So those data are available. There is nothing that hemispheric sunspot data are available. One can check it. And I have seen there is an asymmetry, but it fluctuates. Some cycles the north is more active, some cycles south is more active. So at any given point, yes, there is an asymmetry. Solar cycle, of course. So that is there.
Are there any other questions?
Sir, I just want to know that since geostorms carry the charged particle, does it increase the assay regions or boundaries of that, or it temporarily?
No, temporarily, of course, it will change.
But it doesn't mean
that is
accumulation.
You know that you have seen that effect in XPC. So when the storm happens, you see SA extending over a much longer period. No, it will not last for too long because see there is some equilibrium ionization is there. So it will reach the equilibrium ionization after some time. So it will not, long-term effect will not be there. But during that time, of course, it will be disturbed. So that is why I suspect the South Africa also lost 12 transformers, because it must be because they are close to SA. So that must have spilled over. So that of course happens.
Questions? Okay. Is there any questions from our Zoom audience?
Who is there? Only Acharya is there.
Okay, sure.
Hello.
Yeah.
So I just have a quick comment on the GPS and dual band GPS you just said.
Oh.
So actually there are 3 levels of GPS presently for the civilian use, L1, L2 and L5. The L1 is the oldest one, which is single band.
Yeah.
And L2 and L5, they are the dual bands. But
yeah, those things have happened more recently. Earlier,
yes. So the L1 is still the cheapest. The receivers are the cheapest. So
yeah,
most of the
L1 is the cheapest.
you get
That is
all L1.
So now, of course, third frequency has also been added. That is true. But the dual frequency things became, see, the thing is, something is there, and the receiver also has to be commercially available. See, the military fellows may be having those things, but the civil fellows will not get it until some time.
Yes, so
that things I think happened around, and also all satellites, see, because GPS satellites have some lifetime, so they keep launching it. So I think around 2013 or so, they had sufficient number of dual frequency things available. Before that, they did not have that. So that's why in 2003 it was not available. So of course I don't know when this I think this transition between civil and military happened around 2000 or somewhere around that. I don't remember which year it happened, because earlier there was a restriction, but then there was some issues. So after that they removed the restrictions. So everything was available, but then you have to have the receiver for that. And those things would not be easily available. For example, even today, I think all our cell phones have a single.
Yeah, all are mostly L1. High-end ones are L5.
May be having, but all the normal cell phones are single thing only. So that will of course be there. So of course these improvements have been happening because of, so partly because of this, partly other reasons also. So that's why, for example, in 24 we didn't have any, there was no report of any GPS signal loss apart from these tractors, which of course that is a special
probably
thing.
they were L1 only.
No, they are L2.
Yeah.
No, that I checked. They are L2, but they need a 10 centimeter accuracy. So that may not be possible. See, when the disturbance, see, there is some limit to which you can correct.
Yeah, so few meters for, I think, the single band.
Single band, no, single band can go off by several meters. I think it will not be. See, that will not be meters, actually more than that. So that is why for aircraft, I suppose 1 meter may be enough, but that was obviously not enough in 2003, even after augmented GPS. So that is there. Of course, these tractors are something special. So that is a different issue.
Okay. With that, please join me again in thanking Professor for giving a wonderful talk.
So, thank you.
Everybody is invited for having a tea. With the professor.
So anyway, this you will take care. It was interrupted.
But they didn't have any fancy electronics, but I know that Young, which was at L2, the HFI instrument was severely damaged by cosmic rays.
Oh, that is
because the guy